Hello, Woodstock students. This is Mr. Brennan, and I want to spend a few minutes just kind of outlining some thoughts about best fit lines and the meaning of the R squared value. Like, how should we interpret that? Here in this first slide, we've got three sets of data. We've got some black data points here and some red data points here and some green data points there, and you can see they have different arrangements. Let's take a quick look at the black data. For any set of data, one can find the best fit line, the line that minimizes the differences between the line itself and the actual data points. I've just eyeballed it here, but whenever that gets calculated by a spreadsheet or a calculator or a computer program, one will wind up with a line that will be of the form y equals mx plus b, where b, of course, is the y-intercept and m is the slope of the line. Each data set is unique, and so for each line, you're going to get a slope and an intercept. And in this particular case, the green data, the intercept is way down here. It's some negative value. And so while all three of these have positive slopes, it's certainly possible for a data set to trend downward and to have a negative slope. So that's a quick set of ideas about just what you will get when you get a best fit line. You will get a line that has a slope and an intercept, and it's a way of predicting the y value based on the x value. But you can see just in this data set here, the green line would be one that you'd have high confidence in. The red line would be a line that you'd have some pretty good confidence in, and the black line maybe not so much. It wouldn't be as good a predictor. So how well can we predict y using x given the quality of our data? So while every data set will have a best fit line that goes through it, how good that best fit line is at predicting y values is another story. So here's two examples of some data, and I've kind of drawn in a best fit line through each of the data sets, okay? In the top one, the R squared value, which is a measurement of how good a fit this line is, the R squared value would probably be about 0.1, maybe even less. R squared will range from 0, which is kind of the worst fit and would represent random data, and 1 would be a perfect fit and would be a perfect linear set of data points. In this case, R squared is probably somewhere around 0.1. I didn't actually calculate anything. I'm just kind of guessing here. But what that means is that x, the value of x here, can predict, in some sense, can predict 10% of the value of y. In other words, 90% of the value of y is sort of based on or depends upon other things, depends upon things other than whatever x is. So typically for the Mercury project, y would be your concentration of mercury, and x could be any number of things. But in these kinds of cases, if your R squared value was 0.1, we'd interpret that as a 10%, and that the 10% of the value of the mercury concentration could be explained by this particular, or I should say predicted by this particular x value. Okay. If we look down below here, we've got a little typo here. Let me correct that. If we look down below, R squared is probably around 0.85, or maybe it's higher. But here, the value of x is a very, very good predictor of y. 85% of y can be predicted, if you will, by x, with only 15% of y's value sort of depending upon other things. So it's a nice way to put a number on how much scatter there is in your data and how well x winds up predicting y. Okay? So we'd love to see R squared values of, you know, zero point 0.5, zero point 0.6, zero point 0.7 and higher. As you're probably learning, mercury concentrations is a very, very complex variable, and it depends upon a lot of things. And so looking at any one particular thing probably means you're only getting a portion of the explanation of mercury concentration. Okay? Hope this has been helpful, and good luck with all of your work.